Alright, so this section is on wave mechanics and covalent bond formation. So here I drew the combination of two fluorine atoms. So if we're believing this red is a p orbital, we can see the two p orbitals come together and then morph into one giant orbital. This is called a sigma bond, or a sigma bond, or a hybrid orbital. So first we're going to learn some vocab. So if for example, this is a sigma bond right here. Now if we do a double bond, like oxygen, one of the two is a sigma, the other of the two is a pi bond. Now finally, if we do a triple bond, like that guy, boom, one of them, the middle one, is a sigma, the outer two are pi bonds. So this is important for counting bonds, but you will in all likelihood be asked in at least one or two multiple choice questions on the test, on the AP exam. But you'll also be probably asked one or two about hybrid orbitals. So this is just a visualization of or diagram of the orbitals overlapping. So that's them. That's two fluorine molecules making a sigma bond. Now personally, I think just that one is enough, but your book also has an example of a pi bond being formed, a sigma and a pi being formed at the same time. So yeah, alright, anyways, moving on to hybrid orbitals. So the hybrid orbitals are kind of a pain, but it's going to be a little shortcut way to do it. The way I just remember it is anything sp3 is a sigma bond, sp2 is a sigma and a pi, and sp makes a sigma, comma, a pi, and another pi. So it's really just a triple bond. So the way I remember it is I pretend. Alright, so to show you an example of an sp3 hybridization, we're going to start with a carbon. Now if I ask you to do the electron configuration, we all know that's a S, 1s, 2, 2s, 2, 2p, 2, which you would figure out on your own when you were doing this. But the fast way to do it, there's 6 electrons here, and carbon is the 6th element on the table. Anyways, well, we all know carbon makes 4 bonds though. Well, how can we get this to bond 4 times with something else like hydrogen? So what's going to happen is the s orbital and the p orbital, they're going to make a hybrid orbital. So what this is going to look like at the end is we'll have the normal s, this is s1, then we're going to have it's called the sp3 orbital. Why? Well, it's really simple. We have, oops, I botched that line. Alright, well, so we have your standard 3p orbitals, right? Oh my god, I'll try that one more time. Your standard 3p orbitals plus an s orbital. The s orbital from down here, that guy, moved up to combine with the p. And then one of these guys went to the empty one, and the other one stayed by itself. So now the electron configuration is boom. So now it's pretty easy to see how it would bond 4 times. And that's why sp3 orbitals make nice little single bonds, and in carbon you see them between each of these bonds, for example. These are all sp3 bonds, and they're all sigmas because they're single. So there you go, that's sp3. So I should clarify, the explanations on these that I'm giving are not super important to know, but you should be able to say which hybrid orbitals do which type of bonds. And yeah, so now we're going to do sp2. So let's go back to our little carbon atom. He's s1, bam, bam, s2, p. Well, as you can probably guess from the name, it makes a nice orbital with one s and two p's. Well, let's see our configuration. We have s1. Now we're going to have sp. Now it says s, p, and p2, right? So sp2. Those are going to be filled. Now we're missing an electron. Well, there's still one p orbital left that didn't hybridize. So when this bonds, let's say like with oxygen, for example, to make that guy, the p, this p is what makes the pi bond. This is extra p. So one of these will make the single bond, the sigma, and that guy will make the pi bond. So that's why sp2 is a double bond. Now if you've learned anything from the last two slides, you'll probably know that we'll make a sp hybridized orbital. So let's get our original. This is s1, or 1s, this is 2s, this is 2p. Alright, well let's see what it turns into. We get our 1s. Shouldn't be up, I'm just leaving room for me to draw an example molecule in a minute. Then you get your sp, 1s, and then there's 1p, so those will both be filled. And then now we're up to our p, where there's still two little shells left over. So those each get one also. Now, this makes a triple bond. So if we have the C N bond that I drew earlier for Cn minus, or cyanide, we see that both of these will make pi bonds. And then these guys will make sigma. Well, because this is an ion, it has an extra electron. One of these is full. So that's why you don't see any lone pairs. But if this hadn't been an ion, the other sp orbital would have been used to bond a hydrogen or something with an easy little sigma bond. But one of these two will make the sigma bond between the carbon and the nitrogen, and then these two will make the pi bonds. Well, the sp orbital also gives us another option. So if I draw CO2, whoops, that's not the way to do that. CO2 with its nice lone pairs, we see there's two sigma and there's two sigma bonds and there's two pi bonds. Well, what does that sound like to you? That's sp orbital. This one will make a pi bond, that one will make a pi bond, so pi bond, that one will make a sigma, and that one will make a sigma, so sigma, sigma. So sp orbital is used for a triple bond or two double bonds. So yeah, it's not too difficult. You just have to be able to visualize the sp orbital and see how many bonds it can make. Alright, so now there's something called sp3 dihybrid orbitals. This only happens once you get into the third row of the table, and you start seeing molecules that do actually have d orbitals. So I'm going to use phosphorus for my example. So phosphorus, the electron configuration, we'll just start with the neon in brackets. We'll just do the last 5. So this is 3s is going to be full, and then 3p, p is, there's 3 there, and it's number 15, so it's 3p. Alright, now what phosphorus can do is it can actually make 5 single bonds. Well, you're probably wondering, how is this possible? If you remember from other videos, there is the, if I get my pen to work, there's a d orbital up in the distance that has 5 spaces on it. But because of the way electron configurations go, it's actually in the 4th level wall, or in the 3rd level. The D is just too high of an energy level for us to access right now. Well, with the hybrid, as you can see from the name, D, there's not D2 or anything. One of these orbitals is going to come down and join the P and the S to make sp3d, which gives us 5 spots. So then our new configuration will be, we'll have neon, and then it'll go sp3d, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And so that's why phosphorus make 5 bonds. So you'll see phosphorus fluoride or pentafluoride. And that's why phosphorus can bond 5 times. Now, this is a rarer occurrence, but it is still important to know. So, there you go, that's sp3d. Alright, well, this is the last one, I promise. So for this one, we're going to use sulfur as our example. So again, we're going to start with neon, then 3s, 3p, 1, 2, 3. And remember, sulfur is 1 after phosphorus, so it's going to have 1 more. And then D up there, 2, 3, 4, 5. Alright, so now the new way this is going to go is, as you can probably imagine, now that you've probably picked up the pattern, you're just adding up the imaginary 1 there, plus the 3 plus the 2 to get 6 spots, which is the fast way to do it. Or you can draw it out like this, neon, and then the 1s, the 3p, and the 2d. Let's get your sp3d2 hybridization. So one of those is going to move over to the empty D. Boom, 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 boom. 6 bonding spots. That's why you get molecules like sulfur hexafluoride. And there you go. That is hybridization for you. That is the end of chapter 5. Now remember, this is a kind of complex part of chemistry, but you gotta hang in there because it's nowhere near as hard as it gets. In fact, I think the next chapter might be stoichiometry. We're gonna start doing some math. But for now, yeah, stoichiometry. But for now, they're your hybrid orbitals.